Okay, so first I would like to thank the organizer of the conference for the invitation. So I'm working in Geneva, and I'm mainly doing now Bell non-locality and self-testing. But today I will present a work I did at the beginning of my PhD with some colleagues in Geneva, so Florian Fauris, Tomer Barnea, and Nicolas Gisin, which is about a concept we called macroscopic quantum measurements. So in Geneva, we are interested in macroscopic quantum states. So we want to see whether it is possible to create states which can be considered as macroscopic and quantum from an experimental point of view, but also from a theoretical point of view. So how can we justify that theoretically that a state is both quantum and macroscopic? But here the question is a bit different. So we focus not on state, but on measurements. So for measurement, we have a quite good intuitive notion of what is a macroscopic measurement. But most of our intuition about macroscopic measurements is incompatible with quantum mechanics. So a basic example is, for example, that we cannot measure two non-commuting observables. And then the question is, how can we make quantum measurements macroscopic, and how can we theoretically tackle the question? And yeah. So to answer that question, we decided to really focus on a specific case of measurement. So we considered the case of the measurement of a direction. So in the following, we'll consider a state. So I will call it a magnet, but more precisely, it's just an ensemble of 1/2 spin which are aligned in some direction. And from this, we'll try to see how we can measure this in a macroscopic quantum way. So a macroscopic quantum measurement should satisfy some intuitive characteristics of our intuition of macroscopic measurements. So for example, it should be non-invasive, it should access to a large amount of information, and it should be also collective and something which is realizable physically. So in that talk, I will first talk about direction estimation and introduce all the formalism which already exists about direction estimation. And I will use it later when I will introduce a measurement model which will be our macroscopic quantum measurement. We'll study that model for some states, perfect states, which will be thermal states of 0 temperature. And then we'll look at other states, so a relaxation of our hypothesis. And we'll consider some thermal states of non-zero temperature. And at the end, we'll relax other assumptions about our macroscopic quantum measurements in order to study what I call repetitive ultra-weak measurements. So first, direction estimation. So a picture of the problem is this. So we have a state, a magnet, and we measure it. And out of this measurement, we obtain a result. And out of this result, we try to guess the direction in which the magnet was. So as I said, I'm more working on Bell non-locality. And in Bell non-locality, we always have Alice and Bob. So with this, I'm a bit lost. And I directly introduce Alice and Bob. And I look at this problem as if it was a game. And in that game, we have two parties, so Alice and Bob. And Alice chooses a random direction u, uniformly. Out of this direction, she creates a state, rho u. She sends it to Bob. And then Bob has some measurement device. characterized by a POVM OR, and with this measurement device, he measures the state and guesses a direction, and we choose to take the subscript of the POVM to be the output of Bob. Okay? And then when the game has been played once, we want to give a score to Bob, so how well did he guess the direction, and the guess will be taken to be the scalar product between the input direction and the output direction. So there are many other conventions for the score which exist, so we could have taken this, which is just the fidelity between the two qubit states. We could also have given a maximal score for Bob when he exactly guessed the direction, and a score 0 when he doesn't. This is maximum likelihood, but here we focus on that score. So we make some more assumptions. So the assumptions we make are that, in fact, Alice doesn't choose any state. She has a pre-established state of n qubit. Sorry, it's j equals n over 2. And that state points in some direction z and is invariant under particle exchange. So we suppose that there is no preferred particle in that state. And then she rotates it in the direction nu, and she sends it to Bob. And we suppose also that Bob's measurement does not favor any direction or particle number. And then with this, we can prove that his measurement operator can be written as the rotation of the measurement operator associated to answer direction z. So then the mean score of Bob will just be the integral of all possible inputs and all possible answer of the probability of the answer knowing the input times the score Bob obtained with that input and output. So in that formula, we have, of course, the rotational symmetry over the states and over the measurement. And with that symmetry, we can, in fact, write it in a very simple way where I have just two operators which appears. So a first one will just characterize Bob's measurement and is his measurement operator for direction z. And a second one is that gamma matrix, and it is defined just as an integral of the states and some cosine. So a really important hypothesis in that formalism is that we have covariance. So what I call covariance is that the state as well as the measurement operators satisfy the conditions that there are no direction which is preferred and there is no particle which is preferred. So then these operators will commute with the total spin and the spin in z direction. And a very convenient way to study the problem then is just to go to the basis which co-diagonalize those two operators. So where we have three indices, one alpha which is about the multiplicity and which just talk about which particle we are considering. So of course, as no direction and no particle is preferred, in this will just be a spectator of what we do. It will never appear in our equations or just as like something which does not interfere. So often I will not write it. We also have the total spin, which goes from j, which is the number of spin over 2, to j minus 1, j minus 2 to 1/2 or 0. And we have the total spin along z. And now if we, so alpha is a multiplicity. And what we will see is that as all directions are equivalent, we can really consider each j components of total spin j independently. So then, with this, in fact, there is a really simple way to write the score. And it's, well, it was a well-established result, maybe not over that form, but it was already known, of course. And we can really show that the score which is obtained by Bob can be considered or can be seen as the score he would obtain playing at many different games, each of the game corresponding to a different value of j, and with some coefficients which corresponds to a normalization coefficient, a coefficient which is only about the quality of the state for the guessing, and a coefficient which is only about the quality of the measurement for guessing. So we have a sum over j, and then that term only can be seen really as Bob playing at the same game, but now with a number of spin which is 2 times this small j. And then he's playing with a density matrix, which is just this rho tilde matrix. And this rho tilde matrix is just the component of our state over this vectorial space. So the component of our space which has a total spin j, which is, of course, renormalized. So this is that factor. That factor is really about our measurement, OJZ. So this is the component of the measurement over that subspace. And then we have a normalization factor, which corresponds to, well, how much of the state rho we have into that subspace, and what is the multiplicity of alpha. So you can see in that formula really that now to optimize this, we have really to consider independently the state and the measurement, because we have a product structure. So whatever the state is, the measurement, the optimal measurement will be the same. Okay, so now the optimal measurement and states. So to find the optimal state, we just have to maximize that term. So you see that we have just a trace of Sz, which is diagonal in the Z basis, and our operator. So we really have to maximize the component of that matrix over the first diagonal element of Sz. And well, this is obtained with that state with a small j. But as we also have a normalization coefficient which is important, in fact, the sum of all those traces should be 1. So we should, the best is to put all the weight in the highest j, so to really take that state and all the other components to be 0. In that case, so we obtain a more simple expression for j. And we can also look at the optimal measurements independently of the state. We have to maximize that term. And you see that to maximize that term, we just have to maximize the first diagonal coefficient of that operator. And in fact, we can prove that this is a well-defined P of M. And with this, we maximize that term. So then when we take the optimal state and the optimal measurement, we obtain a score which is, in terms of fidelity, n+1 over n+2. So now, we have seen what is what is the optimal measurement and what is the optimal state. Now, if we are given a measurement with some state, we may want to ask the question how optimal our measurement is. So a way to tackle that question is, well, just to do some asymptotic development of G, and see that the first coefficient in 1 over G is 1. And then for a given measurement with the same optimal state, we will develop J in the same way. So we'll define epsilon j to be this, and we'll say that our measurement is optimal if this goes to 1. Because, yeah. Okay, so I have introduced direction estimation. So now I will introduce more specifically so the measurement model we call macroscopic quantum measurement. So first, so our model is inspired from the pointer measurement. So I will first reintroduce what is the pointer measurement. So pointer measurements are a way to measure observable in a more or less weak way. So in that formalism, we suppose that we have a physical system, which is quantum, and which is characterized by a variable, let's call it a position. And our physical system, our pointer, is initially in a superposed state of all those positions, defined by some function phi. And here we'll take that function to be a Gaussian. So this is what we'll use to measure a state. So the state we measure is a density matrix ρ. And we have some observable A. And then what we do is that we couple our system to our pointer with some interaction Hamiltonian, which is given there. So our initial pointer has some width, given by the width of the Gaussian. And then, thanks to that interaction Hamiltonian, the pointer will move to the different eigenvalues of A. So if, for example, A has eigenvalues 1 and -1, the pointer, after the coupling, will be superposed into two Gaussian, which are centered in 1 and in -1. So then if we measure the position of the pointer and try to guess what was the value of A for our state, if delta is really small, it means that our two Gaussian centered over 1 and -1 are picked. So we'll obtain basically either +1 or -1, and we'll be able to deduce the value of A over ρ. But if delta is really large, then we'll obtain any value of x, and out of this we cannot guess anything about A. So it's really a way to go from a projective measurement of A to no measurement by tuning lambda. So this is the pointer measurement, and so what we considered is a measurement which is based on that model of pointer measurement, but it's a bit different because now our coupling Hamiltonian is the sum of 3 terms. So it's a bit as if we were trying to measure at the same time Sx, Sy, and Sz by moving a 3D pointer in 3 directions. So we have a pointer which is in 3 directions, and it will move thanks to that Hamiltonian in some directions. And of course, at the end, we'll measure the position of the pointer. So measuring the position of the pointer, we can write the cross operator and the P of M elements. And of course, this must be covariant because we don't favor any particle number or direction. So this model can be seen as an Arthur-Kelly model. So Arthur and Kelly introduced that model to measure first x and p, and it was already introduced by Dariano and Okay, so now we have this model, and we can try to see how it performs for direction guessing. So at the end, we obtain any r, so not of length 1, it can be of a different length, but what we do is that out of this r, we just make a guess, which is either plus the direction r or minus the direction r. So in that case, so for small value of n first, what we obtain is are those curves. So in dashed line, I have the optimal value for the different n. And in fact, we observe 3 regions. So for delta going to 0, it is possible to prove that, in fact, our measurement is equivalent to take a random direction, measure the spin in that direction, so measure the spin operator in that direction, and then answer plus that direction if you obtain a positive result, and minus that direction if you obtain a negative result. So this is what we have there. And then, so we have a fast decay of in order 1 in delta. And then, so we have something which is strange and which we were not able to explain. But, okay, so it's like this, and we have no intuition about this still, which is that this curve grows again in delta. And for a delta which is of order square root of j over 4, at least for large j, so j being n over 2, we obtain a score which is close to the optimal one again. And then for large j, the score decreases again, which is a bit trivial because we are doing no measurement, in fact. Okay, so this is what we obtain for our model with small j's. So now the question is how it behaves with large j. So here it's a bit more complicated, but what we did is that, so we took that expression for the cross operator of our measurement, and we performed a host chain pre-Markov transformation over it. So just approximating the spin operators with some ladder operators and approximating that state with the vacuum. And with this, we were able to numerically estimate those cross operators and at the end the score for different value of j, so of delta. So we concentrated over those deltas. And yes, so we also had to do some Taylor expansion. So with this, we just estimate that coefficient, but in fact, it is the most important coefficient in that expression too, because this is the coefficient which is associated to the biggest score. Okay, so for large j, we did this and we took delta equals square root of j over 4. And we estimated the score from the first coefficient. And what we obtained is a scaling factor, which is, so this is the red curve going to 1 with the optimal measurement, but which is now not exactly going to 1. And this shows that our measurement is in fact not optimal to measure a direction, but if we compare it to other schemes, it's not that far from optimality. So now I will tackle the question of robustness. So what we have seen is what we obtain in the case of a perfect state, which is just a state of n spins which points in the same direction. And now we'll try to relax that assumption and ask the question, what happens if our state is not perfect anymore? And so you can see also that in our model, it's really important to take a delta which is equal to square root of j over 4, which is corresponding to that strange region of our model. But we can ask the question whether, well, this is not really intuitive, that we have to really tune quite well that delta. So we also looked at some relaxation of the model, trying to find a way to obtain the same behavior without making that optimized coupling. So, so as I said first, we looked at direction estimation optimality for thermal states. So we can introduce now thermal states, which are given by this formula, where beta is 1 over the temperature, which can be decomposed, of course, in the alpha Jm basis. And we see that at 0 temperature, in fact, we have our initial perfect state. And at non-zero temperature, many different values of J will appear. And in fact, all those values will appear around some J equivalent, which is satisfying this. And now we have a problem, which is that, well, we saw that to obtain the best score, we had to look independently at each value of J. But with our model, we can tune delta in order to tune it for one of the J, but we cannot at the same time, with one measurement, choose different values of delta, which all will be adapted for all value of J's. So in that case, we could take delta equal square root of J over 4, but in our case, it is not possible to do it for all the possible value of J which appears. So what we do is that we take delta is equal to the square root of this equivalent J. And so, well, in that case, we looked at what we obtained for the score. So this is the rescaled difference of the score between what we obtain with a perfect measurement and what we obtain with our measurement with a well-chosen delta. Okay, so now I will go into the model of repetitive ultra-weak measurements. So we saw that in our model, we really had to tune delta, so the width of our pointer, in order to obtain a good fidelity, and that if we don't do that, we cannot obtain a satisfying score for our direction guessing. So in order to see if this hypothesis can be relaxed, so if we can avoid that hypothesis, we went to a different model, which is a model of repetitive ultra-weak measurements. So now we'll consider that we have many different pointers, which look the same as what I introduced, and we'll couple each of those pointers to our system, measure all those pointers, and try to guess the direction out of this. So we have many 1D pointers, which are so of that form, and we successively couple those pointers to our system in some directions W with that Hamiltonian. And now we suppose that we have a coupling which is really small, which is, yes, really small, associated to a really large value of delta. So we can first look at what happened when we couple in all our pointers in the same direction. So when we couple all our pointers in the same direction, this has to be compared with the optimal measurement when we are restricted to one direction. So when we are restricted to one direction, it is not difficult to show that the optimal scheme is just to measure the operator Sz and to answer plus or minus Z. And in that case, we obtain a score which is going to 1/2 for large J. And in our case, where we couple all those pointers to our system, we can, all the operators will commute because they are all diagonal in the Z basis. And we can solve this and find a formula for J. And what we can check is that in fact, J is optimal for a large number of measurements. So if we measure enough time, our system will obtain an optimal J with the scaling which is given by that formula. So this is for the coupling in a single direction, and now we can look at what happened when we now couple our system to different pointers which are successively in alternated orthogonal directions. So we will couple our system to a pointer which are in the direction x, y, z, etc. So for this we did a numerical simulation, and so we should look at this as where we have a system and each measure will acquire a small amount of information about that system and will weakly disturb the state. And we'll see how much we can guess the direction. And the guessing procedure we take is that we attribute really the same weight for all of those directions. So this is suboptimal, but we really wanted to keep the things simple. So in the following, what I will do is that I will consider different value of t, so the total number of measurements, and for each value of t, we'll guess the direction of answer from just all the results from 1 to t. And we'll just take the mean over all those results. So when we do this, so here's what we obtain for a value of n, which is 20. So if we fix the delta to be 3, for example, we see that for a small value of t, the fidelity increase and then it decrease. But this is quite straightforward because when t is small, we have done no measurements, so we have no information. And after a significant number of measurements, will disturb the state, so the answers of the measurement won't give any more information. So as we still take them into account, the fidelity decrease, and we have some optimality between this. So what we see is that, in fact, the maximum is obtained for some t max, and the scaling of this t max in function of delta will be of the same kind of what we obtained in the 1D case. So as you can see, if we increase delta, we have less coupling, so we get less information. So we need to measure the system more in order to be able to guess where the direction. And but this can always be compensated with sufficiently many measurements, and the scaling is given by this, which is what we obtain in the 1D case. So then what we can do is see what is the score we obtain for different value of delta. So if the delta is not of the good scaling, so for example delta of order 1, then we cannot obtain a good score. But when we take delta small enough, then this scheme obtains quite good results. And we can also look at that value of epsilon n. Okay, but we could not compare this to our first case because of numerical difficulties. So with this, I would like to thank my colleagues. So from Geneva, Nicolas Gisin, Tomer Barnea, and Florian Floris. And I'm happy to answer to your questions.